Welcome to this session, and this is a continuation from Centroid, which is nothing but the moment of inertia. Moment of inertia is also called as second moment of area, and which is an important geometrical property of an area. And most of the structural elements have been based upon the concept of moment of inertia. It has been used for the analysis of stresses of in beams in this. It has been subjected to check the strength of the material, and it has also been used for the analysis of pressure on some submerged object in hydraulics. So to begin with, there are few theorems that we should learn before proceeding to the actual numerical problem that we need to solve for moment of inertia. So first theorem is parallel axis theorem, and next theorem is perpendicular axis theorem, and one more important concept and the parameter is the radius of gyration. So these are the three important parameters that we should learn to study or to learn in detail what is the actual concept of moment of inertia. So to begin with, we shall have a theorem what is called as the parallel axis theorem. So first we'll have a proof of parallel axis theorem, and then I shall say what is the statement of the parallel axis theorem. To learn what is parallel axis theorem, so we shall consider an area which has been placed in the x and y plane. So consider a lamina which has been placed in the x and y plane, placed along x-axis at a faraway location. Now, as we already know what is the centroid of this particular lamina, if it has been a regular geometry, the centroid will be known to us, and at particular location of the centroid of the whole lamina, we shall call it as y bar with respect to the x-axis. Then within this particular lamina itself, we shall consider a small elemental area, and that particular elemental area will be called as dA, and the location of this particular elemental area with reference to the centroidal axis, I shall call it as y. That means this dA will vary along the upward direction, along the downward direction. So this dA will vary along the upward direction. It is towards the top fiber and towards the bottom fiber. When it moves towards the top fiber, y will be positive towards the extreme side. Likewise, the same elemental area, when it has been moved towards the bottom fiber here, then y will be towards the negative direction. So when it has a transition point, at this particular location, when it coincides with the centroidal line, the y value would be 0. So that is what is the significance that will occur, and it will be the limit of integration that will be coming into picture when we substitute for this particular y. Now to begin with, the moment of inertia. The moment of inertia parameter is generally been represented as I, and if I have an element which has been placed in x and y plane, so to begin with the centroid, it is nothing but if I have a moment that has been considered with respect to x-axis, then it would be Ixx is equal to y dA. Likewise, if I want to find out the moment with respect to y-axis, then it will be Iyy is equal to integration x dA. So first time integration will be getting it as centroid. So second time multiplication, this will be integration x square dA. Likewise, this will be integration y square dA. So Ixx from this particular first principle, Ixx would be is equal to integration y square dA. Likewise, Iyy is equal to integration x square dA. So the point to be noted here is when I want to calculate moment of inertia with respect to x-axis, y will be the perpendicular distance that I shall multiply. Likewise, when I want to find out moment of inertia with respect to y-axis, x distance will be the perpendicular direction that I will be multiplying. So these are nothing but the perpendicular distance. So that means for each and every axis, I need to find out the perpendicular distance. So if I happen to find out Ixx, then I shall be multiplying y as the perpendicular distance for the elemental area. Likewise, if I want to find out the same element, if I happen to place it along the y direction, that is y axis, then in that particular condition, the moment of inertia of this particular axis would be integration x square dA. Now the moment of inertia of that particular same element area will be integration y square dA. So with reference to Ixx, the moment of inertia would be integration y square dA. Now this y square is nothing but the total perpendicular distance that needs to be considered with respect to x-axis, which will be integration. Total distance of this particular elemental area with respect to x would be y plus y bar. So substitute with the same y plus y bar the whole square dA. So this is what is the moment of inertia with respect to x-axis. So Ixx would be, so integration, you can expand this particular term as the term of a plus b the whole square, which will be a square plus b square plus of 2 times of ab. Likewise, when I expand this, this will be y square plus integration y bar plus square plus integration 2y y bar y dA. So everywhere dA shall come into picture. Now we need to consider this particular terms, that we shall have the final form of the moment of inertia with respect to Ixx. So Ixx will be integration. So this particular term, I shall consider each and every independent term. So integration y square dA. So y square dA, please refer back here, is nothing but Ixx. Now y square dA is nothing but the centroidal portion. So this will be called as Ixg, that is moment of inertia with respect to the centroidal line. Similarly, if I consider the second term here, y bar square, that is y bar is nothing but the centroidal for the second area. Now y bar is constant here, y bar value will not change. For example, if I consider a rectangle section, whatever may be the dimension, that centroidal position will be fixed along the x direction, along the y direction. That is, along the y direction it would be d by 2, along the x direction it would be b by 2. For the centroidal distances for any section, if I happen to consider a triangular section, then in that particular condition, y will be fixed as h by 3 and x will be fixed as b by 3. So this y bar will remain constant irrespective whatever may be the type of area, and it will be integration dA. So this will be y bar a, that is y bar square a, y bar square dA. So y bar square a. So this is what is the second term. This is first term. This will be the second term integration part. Then coming on to the last integration term now. Now the last integration term, it will be integration 2y bar. Now 2y bar, the integration term will be, what will happen here is, y when it reaches towards the top fiber, it will be plus of y. When it reaches towards the bottom fiber, it will be minus of y. When it coincides here, it will be 0. So this last term, which is nothing but the third term, would come out as 0. Third term would come out as 0. So Ixx would be integration. So y square is nothing but Ixg. The second term, y bar square when I take it outside, integration of dA would be a. So this will be a y bar square. So this is what is the value of moment of inertia. Now what has happened here is, the axis which I considered as a reference axis is called as Ixx. The axis which passes through the centroid of the whole lamina will be called as Ixg. So likewise, if I consider a rectangle here, axis which I have been considered for the derivation of the centroid is called as Xx. Then after the derivation, I calculated the value of x bar and y bar. Once I calculate the value of x bar and y bar, that is d by 2 and b by 2, I can have the freedom to again choose one more referential axis, and that particular one more referential axis will be passing through the centroid. Whichever axis passes through the centroid and parallel to x-axis will be called as xg. And likewise, whichever axis passes through the centroid and parallel to y-axis shall be called as yg. Now there are two referential axes. One is called as xg and yg, other one is called as xx and yy. Xx is nothing but the centroidal distance which has been placed far away, which is a referential centroidal axis. Xg and yg are nothing but the centroidal axis which passes through the centroid of the whole lamina. Likewise, this is a relationship that we are going to derive between Ixx and Ixg. Ixx is an axis which has been placed far away location. Ixg is a centroidal axis line, that is the centroidal moment of inertia axis line which passes through the centroid of the whole area. So what moment of inertia statement, that is a parallel axis statement, says is? So parallel axis statement says is the moment, kindly listen carefully, moment of inertia of any area, about an axis in its plane is the sum of moment of inertia about the parallel axis passing through the centroid of the area and the product of the area and the square of the distance between the two parallel axes. That means the distance between the two parallel axes is nothing but y bar, and product of the area is nothing but the product of the area and the distance between the two parallel axes is y bar square, and it is nothing but the centroidal, it is a sum, that is the centroid between the two parallel axes. Two parallel axes is, one is Ixg, other one is Ixx. It is nothing but the equation between Ixx and Ixg. So this is what is the moment of inertia, as it has a relationship between the two parallel axes, that is Ixx and Ixg. We call it, that particular theorem, as parallel axis theorem. Likewise, we need to find out this is parallel axis theorem. We need to have a relationship for the perpendicular axis theorem. Please do remember, Ixx is equal to y integration y square dA. Iyy is equal to integration x square dA. Now we need to have the solution for perpendicular axis theorem. To have the solution for perpendicular axis theorem, consider the same area. Now earlier I had considered an area along x and y axis. The same area, if I happen to place it at a far away location. So before now just for the parallel axis theorem, this particular axis was being considered with respect to x-axis. Likewise, if I consider with respect to y-axis here, this particular area will also have a centroidal along the y direction. When it has a centroidal along the y direction, this particular area shall be placed at a distance. It is placed at a far away location as x bar and independent area as x. So when I consider moment of inertia along yy, then it has a relationship between y and yg. Now what is yg here? Yg is nothing but the axis line which passes through the centroid along the y direction. So Iyy is equal to Iyg plus the second term is the area of the whole area multiplied by the distance between the two axes. The distance between the two axes will be x bar, that is one axis is yy, other axis is yg. The total distance between the two axes will be x bar. So this will be x bar square. So this is what is the distance, that is the relationship between two parallel axes and the perpendicular distance between the two axes, which is nothing but x bar square. So this is what is the parallel axis theorem that we are going to consider along the x direction. This is from the second principle. When we integrate and then separate it up, this is what is the solution that we are going to get for Ixx and Iyy. So perpendicular axis theorem, what it says is, so consider an element which has been placed in the x and y plane. The location of this particular elemental area along the y direction is nothing but y. Same elemental area, when it has been placed far away with respect to x-axis, will be x. Then the area of this particular elemental area shall be called as d. The location of this particular area with reference to one more axis, which is nothing but the z-axis, which will be called as z here. So which will be parallel to the z-axis. This will be along the y direction, along the x direction. So by Pythagoras theorem, we shall write it as z square is equal to y square plus x square. And if I consider an area here, this can also be written as integration z square dA is equal to integration y square dA plus of integration x square dA. Now, just before I had mentioned, that is integration y square dA is Ixx. So here this will be written as Ixx, and integration x square dA shall be called as Iyy. Integration x square dA shall be called as Iyy. So this will be plus of Iyy, and this particular integration term will be called as Izz. So this is what is perpendicular axis theorem. So this will be the derivation for perpendicular axis theorem. So this will be used to find out the moment of inertia about the third direction, which is nothing but Izz direction. So what it says is, we need to add up both the moment of inertia to find out the third moment of inertia, that is nothing but the perpendicular axis theorem. So this is what is the perpendicular statement, what it goes for the perpendicular axis theorem. Moment of inertia of an area, moment of inertia of an area about an perpendicular axis to its plane. Its perpendicular axis is also called as polar moment of inertia about its plane. I repeat, moment of inertia about an area about an axis perpendicular to its plane at any point is equal to the sum of, sum means its addition, sum of moment of inertia about any two mutually perpendicular axes through the same point is x and y axis, through the same point means x and y axis, through the same point in the plane of the area. So this is what is perpendicular axis theorem that we are supposed to calculate. Then what is radius of gyration? That is nothing but the third concept, what is radius of gyration. To find out radius of gyration, so radius of gyration is basically a concept that has been used to convert or to equate a moment of inertia to the area. To find out that, consider an elemental area which has been placed far away here, and this is an area and y-axis been placed. This is nothing but a conversion factor that we are going to find out. So Ixx is equal to equate both the unit of moment of inertia. Say what will be the unit of moment of inertia will be. Unit of moment of inertia will be either in terms of meter to the power of 4 or millimeter to the power of 4. How? It is area unit is meter square and distance unit is again meter, as it is to the power of 2 meter square. So total moment of inertia unit will be moment m to the power of 4 or millimeter to the power of 4. Whatever is the dimensional unit that we are going to choose, the same moment of inertia should be considered for the moment of inertia. So unit of moment of inertia is meter to the power of 4. The simple concept is, as I need to equate both, that is moment of inertia and cross-sectional area. Unit of moment of inertia is meter to the power of 4. Unit of area is meter square. If I need to equate both, here I need to introduce one more term, and that particular term will be called as kxx, and the unit of kxx will be meter square now. So in that particular condition, I will be equating both the parameter, which is nothing but kxx. So this kxx shall be called as radius of gyration, which shall be written as kxx is equal to integration. Here it is already Ixx. Here this is units now. Here it is already Ixx. Here it is A, and I have to equate as meter square. So it will be kxx square. So kxx will be equated as Ixx divided by area. So this is what is the radius of gyration along the x direction. Similarly, radius of gyration along the y direction would be Iyy divided by area. So this is what is the radius of gyration along the y direction. So basically, if the area shown in figure, is concentrated into a strip of the same area and is to be placed parallel to the x-axis, and if it is to be equated to the moment of inertia, and that is what is the formula that we are going to calculate here. such that this strip has the same moment of inertia as about the axis as that of an area, and we call it as a radius of gyration. So this is what is the three concepts that we need to learn: parallel axis theorem, perpendicular axis theorem, and the radius of gyration. So here we shall have the derivation for the first section, that is the sections for the rectangle, triangle, semicircle, quarter circle, that will be used as an individual area initially, and which will be used for the calculation of the centroid. So not the centroid first, and then moment of inertia of the whole section. So when we find out the moment of inertia for rectangle, triangle, this is just a glimpse of what we'll have the derivation in the next section. There will be two axes here. One axis is an x and y axis, and other axis will be an axis which will be passing through the centroid. Now here the axis which passes through the centroid will be called as xg, and which is parallel to x-axis, and which passes through the centroid and parallel to y will be called as yg. Here we'll be having a derivation between ixx and ixg. I'll be having a derivation between ixx and ixg, and to have a derivation between both, I'll be using parallel axis theorem. Similarly, I'll be having a derivation between iyy axis and yg axis, and to have a derivation between iyy and yg axis, I'll be again using parallel axis theorem. So this is how we are supposed to find out the moment of inertia along ixx and ixg and iyy and iyg by using the parallel axis theorem. Thank you. Have a nice day.